So I want to thank everyone for joining us here for Advanced Passive Solar Home Design and Tools to Help. This session is essentially a part two follow-up to a basics on passive solar we've done that we'll talk a little bit about. But don't worry if you haven't seen that. I think you'll still learn a lot, and you're still welcome to join us for this. Now, before we get started, we need to say a huge thanks to all of our sponsors who allow us to do the work that we do. So grateful for their work and their products to help decarbonize, especially our top tier platinum sponsor, Rheem, who is helping people decarbonize their water heating through heat pump strategies. If you don't know who we are the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. We're a small but mighty team of 3, and I am the education manager here, and I will be your moderator for today's session. As always, our courses are approved for multiple continuing education units, including our Certified Green Home Professional designation, this one under the Energy Pathway. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. And if you stay for the entire CEU approved session, you can pick up the Passive House, Certified Passive House Consultant code at the end and get that from your certificate. So with that, I'm real excited to welcome our speakers here, who I'll briefly introduce. Debbie Coleman, who's kind of helping us lead the charge and was on our first basic session, as well as Shannon Pendleton and Keith Sharp. So I'll have them introduce themselves and their organization, but welcome everyone. And Debbie, please go ahead and take it away.
Okay, so thank you so much, Brett, and thank you everybody else for being here and my co-presenters, and to everybody, happy summer solstice week. So if you haven't had a chance to watch the basics of passive heating and cooling, our previous webinar, that's okay. We're going to be touching on some of the basics. And we're also going to be moving very quickly because we have so much to cover. I'm Debbie Coleman. I founded Sun Plans. I've been an architect for over 30 years. I specialize in net zero energy, passive solar home design, and I'm an author of the Sun Inspired House. I've designed hundreds of homes with clients across the US and some in Canada. And I'm also very proud to say that I'm a long-term Green Home Institute member, and I'm on their board of directors, and I'm also on their education and technical advisory committee. So I've become to know this team, this small, mighty team, very well. And I'm just very excited about being a member. Shannon?
Hi, everybody. Thank you, Green Home Institute and Brett Little. It's great to be here. I appreciate the decades of amazing planet-saving content that you've been creating, and to Debbie and Keith for co-presenting today. Happy Juneteenth, big day, and happy summer solstice. I'm Shannon Pendleton. I'm also a longtime GHI member and the architectural designer and sole proprietor of Sanderson Sustainable Design in New Hope, PA, which has the new distinction of being a WBENC. Very excited about that. A self-proclaimed building science geek, which means I'm obsessed with better buildings. I alternately co-host with Passive House Accelerator on their construction tech series. And I'm the in-house Passive House consultant for Source 2050, which is an amazing high-performance marketplace. I also volunteer with Green Building United in Philadelphia, my local municipality of Salisbury Township, and our local watershed association. So I'll drop some links in the chat so you can say hi and kick it off to Keith.
Hi, I'm Keith Sharp. I'm a retired professor from the University of Louisville in Kentucky, and retired in Pagosa Springs, Colorado. And you'll hear a little bit about the house that I'm building there. I have for a number of years been doing research on buildings that are 100% passive solar heated and passively cooled. And we'll wait for my presentation to talk more about that. I'm not only a professor, but I've in a family of 4 generations of builders. So I'm always happy to talk about houses. So with that, I'll turn it back over to Debbie.
Okay, so simple course outline. We're going to break the session into 3 parts. First, I'm going to cover simple tools and programs, and then Shannon will cover the CEUS passive house design, and then third, Keith will go over ambient house design. Where at every home is a solar home. Since the sun strikes the roof and the walls, we can either use the sun's light and energy, or we can let it go to waste. So passive solar, it's nothing new. It's grounded in a lot of historical examples throughout the world. Passive heating. The sun can provide 20 to 90% of a home's heating need with very little cooling penalties. And actually it can go higher, up to 100% if you're using ambient energy sources, and essentially eliminating or definitely minimizing the need for HVAC. And typically these 20 to 90 or 100% are verified ideally by actual use from a utility bill or from a solar app if you're off the grid. Passive solar versus active. Today we're talking about passive. Active is PV, it's easy to see, can be applied to a building later, typically on the roof, but can be on the ground. The passive solar features of orientation, windows, and overhangs, they're more subtle, and they must be designed for initially. So basically we're taking the common elements in a building and we're rearranging them. So we're looking at energy that's going to be hitting the south wall versus the energy that hits the south roof. So today we're focusing on the south wall. So the south wall receives more hours of direct sunlight in winter than the north, east, and west wall. So we want to put most of the windows on the south, but we still want to keep that shape compact for overall energy performance. The sun's seasonal movement, it varies from summer to winter. It's a really basic concept in passive solar design, but you can see the sun's path in winter is very small on the building, and the sun's path on summer is very large on the building. In summer, the sun gets very high overhead at noon in the middle of summer. So standard overhangs on the south, can very easily shade. And winter, on the other hand, it drops low. A lot of that sun can come directly in. I like to tell people, there are assumptions. No, you don't want to put passive solar on a bad building. So we want to build with a low energy building shell that's going to briefly above code R values, tightly built home, right size HVAC, balanced fresh air system, and a HERS ERI rating of typically no more than 40 pre-PV. And that's on a scale of 1 to 0, with 0 being really good. And of course, other typical things that would go into a low energy building. Some passive solar rules of thumb coming from the other webinar briefly. The orientation, long wall to south, most of the windows on the south side, 8% is a good starting point. It's really difficult to go above that and have a well-performing building. You can go lower than that. Overhangs, I think for the south, 2 feet is a good starting point. Thermal mass, dense materials in the building to store the heat, especially if the south glass is getting greater than 7%. The more mass you have, the less interior temperature swing you have. So it really kind of comes down to a comfort issue. And then, of course, one of my pet peeves, you want to right size the home design. The small, simple, compact shape will have the lowest energy needs. Rules of thumb. Rules of thumb can be applicable for preliminary design, for simple projects. You can use them when you're buying a home, looking, comparing one to another, selecting an apartment unit. And there's a lot of detail out there in, for instance, this particular design strategies guideline that was based on extensive hourly modeling. It explains the details behind heat loss and heat gain, as well as thermal mass and ventilation, temperature swing, reflectance of materials, and overhangs. So the rules of thumb that we're discussing have come out of extensive modeling. And it'll also show how as you use higher R values, you need less south glass. But I guess the main emphasis here is remember the basics and use common sense when you're using different modeling tools. I like ones that are easy to follow, easy to input, easy to understand the output, even though there might be something really complex behind there. And this was a tool that I used for, well, I guess around 10 years. And after using it so much, it became almost second nature. So that's the point you want to get to, I think, with any tool. And there's so many similar programs that are used in the front design end. That the more architects and engineers I talk to that are involved with passive solar, the more I realize, oh, okay, they all use all these different things in the beginning, but then they all might run it through a Hare's model, and then some of them add the layer of passive house. So yeah, there's still a lot of choice. No one size fits all modeling tool. Each is going to address passive solar differently, and you want to choose the method based on, you know, all kind of project details, but especially when you're getting to the verifier level, and if you're involved with a certification program, identifying that local rater verifier is very important. There can be really challenges in rural areas because sometimes it can be even hard to find somebody that knows how to do a blower door test. This is some 2D free tools that I really like by Christopher Gronbeck. I've been using these for years, and they're fun and they're easy to follow. My favorite is the overhang analysis, and specifically, I like the older version. One of the things I like about it is I like this center image you'll see where you enter the overhang depth, the height above the window, and then the height of the window. And referring to your own wall detail, even if you haven't gotten there yet on whatever particular project you're considering, you can always go back to a past project. And you really want to analyze that roof to wall detail, because as you can imagine, as the insulation thickens at the edge, and as in this example, a jacked up truss gets deeper, then you need a different overhang length. And don't forget the gutter. There's advanced inputs where you can look at it at another level. The overhang, the results page, you can show the percentage of solar gain. What I like about this, you can see right in the middle, 0%. That means May through August, it's almost 0% is coming in through those south windows. But yet you look at the top and bottom of the screen and you see January, March, October through December, and you see there's a lot of sun coming in. If you want to know more, if you like quantity, you can also choose to see the results in different units of energy. Moving into 3D, it seems like most CAD programs these days that are using 3D are going to have something that allows you to evaluate the shading. Once you can enter that geolocation and you set your latitude, you can help determine how the building is going to be affected by the overhang length. As you get a little bit further with the 3D modeling, this was just an example in SketchUp. Moving to Enscape, you can see you can start to evaluate the inside. You can look at the surfaces that the sun is heating. And if that sun goes directly into a material, it's going to store the heat better than if that room is full of carpet and low mass materials and nowhere to go but to make the occupant feel hotter. I really like orienting the house differently in plan view. A lot of times, if you rotate the south wall 10 degrees to the east of south, you'll immediately see in the tools how that south wall starts to be shaded earlier in the day, which is great for summer. Code compliance, I mentioned this just because I think it's a starting point for learning about energy modeling. I mean, we're supposed to be doing this on all projects anyway, but it's a good trainer for learning basic house energy inputs. And you can always look at it to help you determine, hey, just for starters, how much better am I than code? And then from there, another level, which at that point in the project, often there'll be the home energy rater will be involved. So we have the HARES and the ERI rating software. So those are used to show all kind of compliance. But know that they don't always show the solar gain in the results. Ecotrope has a passive solar checkbox that allows you to override the solar heat gain coefficient. And generally, they don't show much difference when you're rotating the plan in different directions because they're generally static models. So don't be disappointed if you rotate that and say, well, you know, why isn't it changing? That's not the goal of this tool. And the passive solar design, it's usually if you try to Google for support or help, it's usually not in there. So you really want to realize the limits of these tools from a design standpoint, but you still want to use them for Energy Star, etc. Here's just an example showing the results of when we rotated the building in 8 different compass directions, how very little changed. This is a tool that's free by NREL. Some people really like this. I have used it, but I found that unless you're a builder and you know the details of the cost that's going into the project, it's less than helpful because it can mislead you and you have to spend a lot of time putting the cost of the components in. But it does take into account passive solar. Okay, so passive solar versus passive house. So any passive solar design can become a passive house. You'll add additional layers of modeling and plan review and verification and testing. And a passive house can be modeled under different types of passive house software programs. It can be certified under one of 2 different programs. And what I've found is that a lot of the designers and consultants are qualified in both, and they will pick and choose the program based on the project. And then finally, in addition, a passive solar home can also be rated to Green Star, to LEED, to Zero Energy Ready, etc. So if you're confused, you're definitely not alone. You know, one program does not preclude the other, and the passive house layer can be added. This is an example project that Tim Ian presented. He had a really good webinar on this particular house, and he showed that 60% of the winter heating needs could be met with passive solar. Tim went on to share an example of a PAPP worksheet, which comes out of the Passive House Institute model. And basically, so it ends up showing the heat loss through the surfaces, the heat loss through ventilation, the total losses, and then the percent of passive solar gains. And on this house, it was 64%. But, you know, they do typically caution, they being users of the PHPP software, to make sure that you break out each window carefully to evaluate the shading, because that's a very important part. Tim also shared with me this other presentation that was done by Graham Irwin, and he's also a passive house consultant, and he is comparing the passive house to some of the home energy rating systems. And if you get time, I strongly encourage you to take a look at that session. So in summary, he did not recommend using the HERS software as a design tool. And you want to make sure you use the right tool for the job. You want to match the model software to the project and to your consultants that are available, and of course to the Rater Verify. And if there's none available, as a minimum, try to find an HVAC sub with a blower door test kit. So a lot of times when you're in these rural places of Alabama where there might not be a lot of energy professionals, for lack of a better word, to choose from, a pretty good approach might be the best for you. And again, in conclusion, with passive house consultants, the passive solar design can become a passive house. So starting to wrap up my part, the goal is for resilience to man-made and natural disasters. So homes that are incorporating passive strategies of heating and cooling, they're going to rely less on mechanical, because those mechanical systems can stop working. when the power grid goes down, when the gas line breaks, when the propane tank is empty, when parts of the PV system, either the panels or the batteries or the inverters, whatever, malfunction, or the HVAC equipment might stop working. So basically, we're working with nature for home heating and cooling. We're utilizing technology and mechanical systems, but we want to be able to survive without it. We need to not forget about the back to basic comforts of airflow, shade, and outdoor living, my favorite. Allow airflow to remove heat from the body and the house with the stack effect. And don't forget to open windows and doors on opposite sides of a space to increase airflow if your HVAC system is not on, of course. Enjoy being connected to nature with the airflow, sunlight, and views. Okay, thank you very much. And now I'm going to turn it over to Shannon, and I'm going to remember to stop sharing my screen.
Thank you, Debbie. Fantastic. I really love seeing that presentation and getting such a great platform to start off from. So thank you. I am Shannon Pendleton, as I mentioned before, and I'm really glad to be here among friends who are like-minded. I'm guessing you've noticed things are getting pretty hot around here, especially on the solar solstice that we're experiencing. So why are we still talking about how to use renewables like the sun? And why have fossil fuels had a 250-year head start? Why do we want to use what's limited and rare and hard to get when we could use what's free and easily accessible everywhere? I think the answer is comfort and power. We as people want to feel comfortable and we want to feel powerful. And that's why we turn our thermostats up and down. So this is a picture of Thomas Edison holding a battery, which I've circled here in orange. And he's holding this battery to his electric car in 1931, where at the same time he had a wind-generated plant in his home. And he said to Henry Ford and Harvey Firestone, "I'd put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that." So I am fully with Thomas Edison on this one, and I'm sure you are too. So let's go back just 10 years ago. In 2015, we wanted more heating than cooling. And even then, trends were shifting, right? We started to see heating going down and cooling going up, even in 2015. And if we want to reach our 2015 to 2050 goals and use our buildings, which are nearly half of the problem, to mitigate this, we have to determine how to use the free parts of the sun, whether that be for heating or for cooling or for power. So what's the difference between passive solar and passive house? They look pretty similar. They are really good form factors. They're both super insulated. And what you'll really notice is that passive is the common denominator between the two. So what does it mean to be passive? It means you can use what's free or you can pay for what's active. And those active systems and those passive systems are very similar. So in a passive solar house, the principles are, as Debbie mentioned, that orientation, the shading, the thermal walls, heating and cooling, ventilation, daylighting, radiant gains and losses. In a passive certified house, it's an airtight exterior wall assembly. So just like wearing a really good jacket, it really saves you from those losses, and it makes the heating and cooling slow down significantly and reduces those gains and those losses. So it's a really envelope first approach. So we're looking at super insulated exterior walls that are airtight. We're looking at super insulated windows that are also airtight, reduced thermal bridges in the envelope so that heating and cooling can't travel through the structure from outside to inside. and an energy recovery ventilation system. And in most homes, we don't have ventilation systems, but in all of our commercial buildings, we do. So this is really making a play to use energy recovery ventilation, which allows you to save that energy instead of throwing it out the window with your stale air. Now, the certification requires you to go all electric, and it also accounts for daylighting, radiant systems, hot water demands, indoor air quality, appliances. And to achieve that certification, both the design and the building have to be third-party rated. So it's not the designer or the builder or this passive house consultant saying you passed or failed. It's a third-party rater saying you passed or failed. So it's a very rigorous building metric. And here's a visual equation of how passive house is prioritized globally. So in Canada and the US, the Pennsylvania Housing Finance Agency, Marin County, California, NYSERDA in New York, and Massachusetts are all using passive house to get the co-reciprocal certifications of Energy Star, ResNet, EPA's Indoor Air Plus, and the Department of Energy's Zero Energy Ready Home. So they're going through these steps to get to passive house. But if we look globally at what the trends are, in Brussels, in Belgium, in Ireland, in Scotland, you can't build any other way. You have to build a passive house. It's not an alternate step code, it's the only code. And so they start with passive house, and they do that because they want to add low embodied carbon materials, electrify everything, source that electricity from a renewable resource like the sun, to get to zero carbon, because zero carbon is now our goal. So the staircase on the left, all above code, should look familiar to you. I've used Green Home Institute's staircase many times in many presentations. And I thought it would be nice to put the Department of Energy staircase right next to it, which both show how passive house relates to other green building ratings and certifications. And what the Department of Energy one is showing on the right is how it also relates to the HERS score. So here's the HERS score right here. So if you start with basic code or get up to some elevated codes or jump up to Energy Star, Indoor Air Plus, Zero Energy Ready Home, you start to go from a high HERS score, which is a home energy rating score, to lower rating scores, with the goal being zero, which is CEUS's motto. CEUS says zero is the goal. And they're really even looking now at more regenerative things than zero, adding energy. So CEUS has come a long way, and the certification has evolved over time, which is one of the main things I love about it. So it's trying to address energy, carbon, renewable and regenerative goals, along with equity and health. And on Juneteenth, I think equity is a big part of that. Environmental racism is real. So there are two paths for certifying with CEUS. There's a prescriptive path and a performance path, which relates to whether you have to do an energy model or you don't have to do an energy model. And for the core prescriptive path, well, let me back up one sec. So the historic baseline, this is like your typical building. If you go for CEUS core, you're really cutting that in half. And you're looking at a fair share glide path. And then 2021, you're cutting that in half. And you're looking at not just adding solar and renewables, but you're looking at offsetting them with renewable resources, regardless of where you get that energy from, whether it be passively from the sun, actively from solar panels or your systems, or if you're purchasing it off the grid. You need to offset that and get to zero to go from CEUS 2021 to source zero. So if you're doing the prescriptive path and you're using CEUS core to get there, the simple solution is you're looking at your climate first. So you're using their climate map, which is right here, to click on your climate set. And right now I'm using Alabama, even though that's not heating dominated climate. It's a great example because It's the default. And if you choose that climate, it will give you all of your maximum and minimum prescriptive conditions for the elements you'll need to account for if you're going to certify with Passive House. So your U value for your window, your solar heat gain coefficient for your window, your projection factor for your window, which determines how much shading it's getting, your recovery efficiency for your systems which are active, like your ERVs or HRVs, your wall R value, which is how much insulation is in your walls, your R roof value, how much insulation is in your roof, whether you have an in-conditioned basement or crawl space, what that R value will be, below grade walls as well, and floors, and then air source heat pump efficiencies for SEER and ratings for those with regard to how efficient they can be. So they put universal requirements on these, climate-specific requirements on these, and building-specific requirements on these. And what that looks like when you apply these in the prescriptive snapshot, which is a calculator CEUS gives you online. You can click on your climate and get these, and then click on this calculator, input a few factors for the number of bedrooms and people, and it will spit out all of these values for you regarding your climate. So it's super simple, and then you just talk to CEUS and they will guide you through the process. So that's prescriptive path. Now for a performance path, you can also do core, or you can do 2021, or you can do 0. So those also have space conditioning requirements, energy and overall impact requirements, solar protection, and fenestration orientation for detached houses. And it also allows you to go through that protocol calculator to create your conditioning criteria and the demands that you're going to have on your heating and cooling, and your heating and cooling peak loads. So if you want to get to CEUS core, you immediately get a result for how many kilowatts per hour per person per year you're allowed to use. So it sets your budget on your energy. And if you want to get to 0, your budget is 0. So that's the simple answer. And when you're really designing toward these goals, you're really looking, I think I skipped a slide. No, you're really looking at designing with an energy modeling tool. So the energy modeling tool that you can use to certify with Passive House can either be the PHPP, if you're certifying the international path, or with CEUS, you can certify with the PHPP, or you can certify with a software called WUFI. And WUFI is made by Fraunhofer. It is a really great energy modeling tool that accounts for all 3 solar radiation measurements on surfaces, along with a whole host of other items, which I'll get into next. But since we're talking about passive solar, this really talks about your global horizontal surface measurements, your direct horizontal surface measurements, and your diffuse surface measurements. 2 of those need to be specified, and WUFI calculates the 3rd. So that's the short story on how WUFI looks at solar gains and losses. But when you're a designer, you're looking at how to optimize these good design principles very early in design and strategize for everything. So with regard to site orientation and form factor, you're going to look at your site and all of your solar orientations, but you're also going to look at water, you're going to look at sequencing, phasing, systems, power, and monitoring. So, you know, just a quick plug for if you're a designer, take these things into account very early. And when you're looking at site orientation and solar, take a look at your building and look at it at every time during your winter solstice and every time during your summer solstice, or at least every 3 hours, and look at what's happening to your building. So this is actually a passive house that is multifamily. It's 2 units. It's a very small view of the roof plan, but you can see what's happening at 9 a.m., 12 p.m., 3 p.m., and 6 p.m. For this client, we had demands on getting daylight into their bedroom during the winter solstice at 9 a.m., which is right here. And we can see that we are going to get light into all those windows, which are located right here on that building. And we're also going to get solar on all of our rooftops all throughout the day. And that's why the roof was designed in this fashion. And we're going to get that in winter, so you know we're going to get that in summer. So this is that same building in WUFI. Well, first in SketchUp and then in WUFI. So in SketchUp, we designed this building by looking at only the surface of the outer edges of what we call the thermal envelope. So that's the outer edge of where the insulation ends. And where that ends, we then assign properties to it. So at the roof, we can assign properties of whether it's opaque or transparent, what zone it's in with regard to heating and cooling, whether its outer side is exposed to the air, or what's called an adiabatic condition, which means the same temperature, the same conditions that are inside, and whether the orientation is facing the proper direction, which is this little red arrow. And then it also calculates the geometry of that surface. So SketchUp is great because it's an easy, fast way to model and assign these properties and get all that geometry calculated numerically. And that's why we use SketchUp. It's got a WUFI plugin. I can assign all these properties. You can see this door has transparent qualities to it, which means glass. It's zone 1, it's outer air, it's oriented okay, and all of its geometry is accounted for. It's casting shadow and receiving shadow. And then down here, I have below grade walls. So they are opaque. They are contacting the ground. They are facing the proper direction when I'm looking at where they contact the ground. And their geometry is also accounted for. They are not receiving shadows or casting shadows. So when I take that model from SketchUp into WUFI, I am now going to account for the climate and source energy and bring all of this in and put it up against my space conditioning criteria for what FIA says my budget is with regard to the envelope area and the interior conditioned floor area, which is the cubic footage, or excuse me, the square footage of the floor area to the interior face of what I'm heating and cooling, which usually means the drywall. So the envelope area is all the way out to that thermal envelope, and the interior conditioned floor area is where my heated and cooled conditioned air is limited to by my air barrier or my drywall. It's also taking the location into account and my limits into account. So this is a snapshot inside of WUFI for this same project. What WUFI looks like is a 4-quadrant energy modeling visualization tool, which is great because the PHPP is a spreadsheet. And for those of us who love our spreadsheets and hate our spreadsheets, we're very happy to jump into WUFI and look at these same numbers and have a visual representation of them. So on the top left, you'll see it's a navigation tree. On the very top, it's a menu and toolbar. And the menu and toolbar, they let you navigate to any function. The navigation tree has branches and twigs that come out that you can collapse and hide or make visible for every different entry screen. So if I click on localization and climate, I'm going to see the results and the status over here in the results and status window. If I click on a visualized component, I can click on the window, the slab, the roof. I can click on anything that's a thermal bridge that's not visualized or visualized, and all of the systems as well. And I can see those results in this results window, right down to whether or not my mechanicals have the performance they need, or my plumbing geometry will allow me to meet my heating requirements for hot water. So with that in mind, then I can also look at the building in the visualization box. I can spin it around. I can click on elements on the visualization box. And when I click on them, it will change the status results and the navigation tree to show me what I'm clicking on and where it's located in both of those windows. So these 3 windows work in tandem continuously based on what you're clicking on to show you what the focus is. This 4th window is the input-output dialog box. And when I click calculate woofing shading, it will calculate everything from the geometry to all of my inputs. And it will either give me green check marks or red X's based on my limits. So my limits are shown with these black hash marks right here. So this limit is my heating demand. This limit is my cooling demand. This limit is my heating load. This one's my cooling load. This one's my source energy. And this one's my site energy if I'm going to get to 0, which we did. So we did reach certification for Source 0 on this project. So I went in and at Debbie's request, I changed the orientation of my building because it's great to see how this impacts a passive house. If this were a passive solar project only, it would impact it wildly. But what you can see is when I change the orientation from south to north, yes, the bars move up and down, especially with regard to my heating demand, because I am taking advantage of the free heat of the sun in winter, and I am shading it in summer. But the heating demand jumps a lot. The cooling demand doesn't jump that much because I'm already shading. I'm already doing other things with my cooling demand. The heating load, it jumps a little bit, it jumps up a little bit actually. But my cooling demand, not so much. And then what you really see is the power of the passive house envelope in this. The envelope is the thermal mass, so to speak, in a passive house. And what it's doing is it's slowing down our losses and gains so that everything that happens internally is totally controlled. All of the air is filtered. You can open your windows or close your windows if you want to, but if they're closed, that airtight envelope, that super insulated envelope is controlling for everything from how your air is filtered to how it's heated and cooled. So this is a look at then how that super insulated envelope can act like a battery, because if your power goes out, a passive house has been known to what's called drift. So the temperature of the inside of that envelope where you want to be comfortable, and the reason you turn your thermostat up and down, that temperature will drift for like a week. And in some cases, passive houses don't turn on their furnaces at all in the winter because that temperature drifts so predictably and beautifully when the power is out, let alone when you have power. So it's a great resiliency plan. And when you look at the peak per load of a typical building on a typical centralized grid, a peak load per building for 4 buildings, when you multiply that across the peak of 4 across 9 buildings, you actually have a peak of 36. So that's what's the exponential growth of a peak load on the grid. So when you talk about battery use and you talk about alleviating the grid or using a battery or using a building as a battery, you're talking about shedding loads and being smart for the grid. So a typical centralized grid, when it's doing load shifting or shedding, takes that 36 down to an 18 on like a central grid signal, if the grid is doing this work. And the sum of that coincidental peak can take it down even further if you look at microgrid demands and take your grid down to a microgrid. That can take the 18 down to a 6. Then this is just using the grid to shed loads. Now, what if you use passive house and the grid to shed loads? This is all from CEUS, by the way, and there's a QR code right here to download the full report. And Lisa White is where I grabbed these slides from, so full credit to Lisa, one of the greatest heroes of passive house. If you look at passive building and that typical centralized grid, instead of a 36, you're at an 18. And if you look at passive building on a microgrid, you get down to 9 coincidental peaks. And if you look at passive house and a microgrid and load shifting or shedding, you get those grid peaks down to 3. So this is how the building acts as a battery and how it alleviates the grid and reduces energy use. And in Philadelphia, our peak loads versus our off-peak loads versus our super off-peak loads through our energy provider, PECO, are 7 times less expensive. So if you're shedding loads and you're using energy off-peak, you can save 7 times the amount of money. And in some cases, PECO will pay you. And if you want to contact me for proof of that, I'll send you a very fun video from a local solar provider where they ran out to someone's house where they installed solar. And this guy is making $450 a month. And he's charging 2 Teslas, 2 Powerwalls, and a typical single family house with 4 bedrooms. So the moral to the story here is passive principles, whether you're doing passive solar or passive house, they are like connected levers that you move down one and the others respond. So what you want to do is optimize what's free and minimize what's active for your wallet and for the planet. So with that, I'll stop sharing and kick it off to Keith. Thank you so much.
And just real quick, Keith, as you're getting your slides loaded up, we're going to go over a little bit here today just to wrap up the presentations. So for those of you who have to get going at 1 Eastern and you've been here, you are CEU approved, and we'll send you the recording so you can watch the rest. But we're going to go over a little bit late, and then we're going to, I hope you'll stick around, and we're going to get into Q&A right after Keith wraps up. So thank you.
So my presentation is going to be a little different in that I want to talk about buildings that are 100% conditioned by ambient energy, and also about a new pre-design tool that we can use before we even start drawing the building. So compared to, let me see if I can, so compared to a conventional building where we use auxiliary energy to keep the house relatively constant temperature indoors, and with a future all renewable grid, that would be with electricity. An ambient house keeps the temperature between a high and low limit with ambient energy only. And to do that, we use a hot source and a cold source, for instance, the sun for heating and nighttime ventilation or sky radiation for cooling. And we regulate the heat transfer between those sources and the house. And when the appropriate source is not available, we use thermal mass to moderate the temperature swings until the appropriate source is available again. This has been possible for a long time. Back in 1948, Maria Telkes built what was one of the first 100% solar heated houses. It uses active solar energy and phase change storage. Harold Hayes' house in Atascadero, California, has an 8-inch roof pond on the roof that gathers solar heat during the winter and rejects it during summer. Paul Shippey's house in Longmont, Colorado is earth burned for reduced losses and has a bead wall system on the windows on the south side where insulation is blown between 2 glass panes to reduce losses. Carl Warren built a Norm Saunders design back in 1986, and that house has remained between 65 and 75 degrees Fahrenheit for all these years. Then there are 2 more modern houses. Jim Riggins' house that started with a Debbie Coleman design. It's near 100% ambient conditioned. And we'll talk more about my house in Pagosa Springs. So if we model the house as a bucket, where if the bucket is overflowing, that means the house is overheating, or if the bucket is empty, that means the house is getting cold. Historic passive solar houses had larger envelope losses than is typical today, which meant that they need needed a lot of windows and a lot of thermal mass. The more modern ambient house approach is to have lower losses, which means that we need fewer windows and also less thermal mass. The models that we could consider for simulating such a house are static and dynamic. And static, though, kind of neglects the thermal mass. So it has an instant response to temperature change. Examples include PHPP, WUFI Passive, Ecotrope, and HEAD. HEAD actually uses an admittance method that kind of approximates the effect of thermal mass, but we can do better. So I'm going to say that these are not appropriate for ambient house. We want to use a dynamic model that faithfully includes the effects of thermal mass. It gives us a gradual response to temperature change. And the complex and general options include BLAST and DOE2, but they're grayed out because they're not supported any longer. Most of the best features of those two programs have been wrapped into Energy Plus. And there's also Transys, which is a very general program that's not just for buildings. Simplified building modeling programs include Energy 10, which was a favorite of a lot of people, but it again is not available anymore. Other options include BOPT, eQuest, and WUFI Plus. WUFI Plus, not WUFI Passive. And Solar Shoebox, which is in a different color because Professor Peters designed this program to specifically simulate buildings that are called free running. That is, they have no furnace, no air conditioner, and it predicts indoor temperature. It's for a 100% ambient conditioned house. A slightly different category is solar load ratio, which uses curve fits of dynamic simulations to give us energy performance results. But the results are only monthly values, and we really need hourly values for the whole year. Solar load ratio was also developed with 1980s buildings, so we're going to cross that one out also. All of these models use from hundreds to even more than 1,000 parameters, so it can take a while to get a case run. But on the other hand, PV watts, which is not for buildings, it's for photovoltaic systems, has only 6 inputs. And so literally in seconds, you can get a result. Now, for example, HEAD, you have to input the geometry of the building. You have to put every window on every surface. There are 20 pages of basic inputs and 8 inputs per window and door, and that's just for the geometry. You need more inputs for thermal properties like the U value and the solar heat gain constant. There are 18 pages of advanced inputs. Here's the window and door input panel. So it's going to take you quite a long time to get your first results. But I hope that motivates the need for a faster and easier to use software tool. Any design process is fraught with a paradox that as we work on the problem, we gain knowledge, but at the same time, we may be making decisions that reduce our design freedom. This carries through to architectural design, where we often design the entire geometry of the house and then do the energy analysis later. That can back us into a corner where we can't get to the performance that we would like to have. So better would be to do a pre-design energy analysis so that we have goals that we can carry through as kind of a specification that we keep in mind throughout the entire design. So how simple can the model be? To our bucket model, I have added the cooling. So these 5 variables are really all that is necessary. And those hundreds or 1,000 parameters for the more complex models are just refinements of these 5 basic variables. And the engineers in the room will realize that with 5 dimensional variables, we can reduce that to 2 dimensionless variables. Pi 1 is the gains over the losses. Pi 2 is a thermal time constant that is the thermal capacitance over the envelope loss. Now, is a little complicated, and we can get perhaps arguably more insight by breaking it into parts, where the envelope loss is the common denominator. We have the solar load ratio, the internal heat load ratio, and the ventilation cooling ratio. If we're using sky cooling, then we would replace VLR with a sky cooling load ratio. Let's look at some of these numbers. First, on the left for our example houses are the dimensional parameters. The peak load can be compared to the passive house standard of 10 watts per square meter. And you can see that the two modern buildings are right in that range. So passive house is a good place to start, but it's an incomplete design. The older houses are a lot more. Internal heat gain has decreased a little bit over the years, but the important thing I want you to notice is that it's significant compared to the peak load. So we don't want to neglect internal heat gain. Thermal mass can be compared to the range for light to heavy conventional construction. And you can see that the two modern houses are right in that range, and the others are a lot more. So often a lot more concrete, and we know the carbon disadvantage of concrete. The solar aperture has decreased a lot. And then our non-dimensional parameters, the solar load ratio and the internal heat load ratio for January, if the sum of those two is equal to 1 or perhaps a little bit more, that means we have enough heat during that month to keep the house warm. And so that is a good target that we can learn from these non-dimensional ratios. The thermal time constant, it represents the number of days that the house can stay warm if the sun is not out. And you can see we're getting away with smaller values for the modern house. The CEUS house is enormous because of that phase change storage. Larger is always better. And for cloudy climates, you need higher numbers, like for the Saunders house in Massachusetts. And the final ratio is the ventilation load ratio. That was 9, which you can get to with natural circulation, except for the Hay house, which used sky radiation. So the pre-design tool, we talked about PV watts. Here is the input screen for PV watts. There are only 6 parameters, and they're defaults, so you don't even have to do anything. You just press one more button and you can get your first case run. You also have to put in the weather data in the previous window. There's an advanced parameters window where you can put in extra things, but you can get results within seconds from PV watts. It's been used 100 million times per year now, and so it's extremely popular. It is really helping people design their PV systems. And wouldn't it be great if we had such a tool for buildings? I'm tentatively calling my tool Ambient Watts, and if you have a better name, please let me know. At the top are those 5 basic parameters. There are several optional inputs as well that you don't have to put in until you get to a more advanced stage of your design. And at the bottom, it's showing the predictions for every hour of the year of indoor temperature. And you can decide what your comfort range is and check the results and see whether they're good, and then try variations. So here are those 5 basic parameters. First, the envelope loss. There's a recommendation for the envelope loss that gives you the passive house limit of 10 watts per square meter, and you can just plug that in. The value that's in the green box is the as-built value for my own house. The internal heat generation per floor area, there's a default there that you can plug in. The net glass area for solar gains, you can start with 5%, or if you're in a cloudy climate, maybe a little bit more. Thermal mass, there's a range for light to heavy construction, and you can put a value in there that's around the middle. And then, as we mentioned, 9 is a good value for the ventilation to load ratio. So within seconds, you can put in 5 values. It automatically does the calculations, and the calculations are done with this simple model in a fraction of a second. So here, for example, is a comparison of my house to the prediction from ambient watts. And maybe the first thing you notice is that it starts out cold, and that's because we were away for the Christmas to New Year's holiday, and there was a storm during that period. So kind of a worst case scenario, but it warmed up pretty quickly to the comfort range, which is shown between the red line and the blue line. And the place where we got the worst match was during the summer, and that's because the occupants were using manual control of ventilation cooling instead of automatic control, which the model is doing. You can see the potential benefit of automatic control is pretty awesome. You can also do this with BOPT, EQuest, and WUFI Plus, not with WUFI Passive. Here's the predictions for the year with TMY data from WUFI Plus. The thing that I want to point out, or at least I'm not an architect, so I'm not used to doing building designs, but this run took me probably about 3 days, mostly in putting in the geometry of the building. So where ambient watts is giving us a result in seconds. I also need to tell you about typical meteorological year data and how it gives inconsistent results if you're trying to get to close to 100% ambient condition. You can think of TMY as being average weather data. We all know that weather varies from year to year. If we use TMY to design a house in Miami, for instance, then for those 23 years that are used to formulate the TMY 2020 data, it overheats for about half of them. Those are the red bars. In Phoenix, however, that TMY house only overheats for 1 year, so very inconsistent results. Madison, Wisconsin, undercools for all the blue bars. It overheats for the red bars, and it does the same in the same year, or does both in the same year for the purple bars. So if you're an architect, and you designed a house with TMY data and it performed like this, you'd probably be getting some callbacks. In Rock Springs, it overheats for most of the years, in fact, up to about 7 degrees Celsius, which is pretty serious. So what can we do? We don't want to use TMY, at least for our final design. What you can do right now, before we have a better solution, is to simulate for real weather data. And we need to probably use at least 20 years to find those extreme years. Once you have them, then you can formulate an ambient meteorological year data that's constructed from the worst winter and the worst summer. Now, for Rock Springs, for instance, we would pick the winter of 2017, take those 6 months and put them together with the worst summer, which is for Rock Springs 2018. And then we've got a single year of data that if we design the house with that AMY data set, the house will remain comfortable for all of those years that was used for TMY. So conclusions, the Pagosa Springs ambient house for 2022 was nearly 100% ambient heated. We used 0.4% wood in the fireplace. It was 100% ambient cool. And in spite of that initial low temperature, still only 2% of the year was below the comfort limit. We can compare that to the passive house standard, where the house can be above 25 degrees C for 10% of the year and still get certified. So this house is performing pretty well. The total purchased energy was just 17% of an average residential building. We don't have solar thermal hot water yet, but once we add that, we could get to net zero with a PV system about 1.5 kilowatts. The pre-designed model really works pretty well. It gives a reasonable match with only pre-designed parameters. And I want to add here a plug for Ambient Energy. Ambient Energy can not only do space conditioning, it can heat hot water, it can cook food, it can do daylighting, it can dry clothes, it can even do refrigeration. It is cheaper in many cases than the alternative of producing renewable electricity and storing it when necessary. It improves resilience because an ambient house will remain comfortable even when the power is out. And it increases energy equity by reducing energy bills. So it should be a part of our national energy strategy. And if you want to learn more about our efforts in that regard, go to the white paper that was a result of a workshop that we held, and the website is there. Thanks.
Hey, thank you so much, Keith, and thank all of you. We're going to go ahead and jump into our Q&A and questions now real quick. Before we get into those questions and get to many of these questions that are coming in here, just a reminder that yes, this session is being recorded and it'll be available on our YouTube channel. You can check back there in the next couple of days, or you can go there right now, hit subscribe and get an instant update when the session is available, sent right to your email. For those of you watching this in the future, but not right now, but on demand, you need to take your quiz with a 10% passing rate to receive your continuing ed certificate. For those of you watching this live, check your spam over the next couple days for certs at gutenbergcerts.com. You'll receive your CEU certificate to self-report there. Make sure you take the survey for AIA so we get your AIA number, and then we will report that. And as those questions are coming in, we're going to get to those questions real quick. A huge thanks to our board of directors, all of our volunteers, our executive director, Jose, Reina, and all of our sponsors who allow us to do this, especially our top tier sponsor, Ream, for air source water heating decarbonization. So yeah, let's get into some of the questions that are coming in here right now. And I just want to pull those up, and I can't seem to do it. So that's okay. I already have a couple off the top of my head. You know, Keith, I wanted to clarify with you on the PV watts, since we have that fresh in our minds right now. The PV watts, as we know it, is for designing active solar systems. So just to clarify so that we're all on the same page, and maybe I'm the only one on the wrong page here, you're saying using the hourly usage data that PV watts yields to get the energy data you need for ambient. Am I putting that correctly? Or what reason are you asking people to use PV watts for?
Yeah, I'm not asking anyone to use PV watts unless they're designing photovoltaic systems. And okay. I think it's just a great tool for photovoltaic systems. But my point was, wouldn't it be great if we had a program that would design buildings for us that was as simple to use as PV watts?
I see. So you're not saying the data from PV watts could also be useful for passive solar. You're just using it as an example of we wish we could use it for something like that, right?
Yeah, I'm kind of using it as a gold standard for a really easy to use tool. Yeah. And if you compare PV watts to BOPT or EQuest, which are supposed to be simple, you see, wow, PV watts is a lot simpler than that. And so with ambient watts, I'm trying to emulate that simplicity that we see in PV watts, and hopefully get to like 100 million people designing homes that require no furnace and no air conditioning.
Okay, thank you for clarifying that. I wanted to make sure I heard that right. And I know one great way people have used PV watts is to work backwards. So they've used it to model the site. They know their limitations of solar income, and they know that's then their limitations to hit net zero. So there is some practical to the building shell of it. If you're trying to be net zero, you're site constrained to that site, and there's only so much solar radiation hitting it. So I've known people who have used it to work backwards and say, we have to have our energy loaded designed to that, right? Like it can't go any higher than that. And so I have seen that method as one strategy for the, it doesn't answer all the other questions. Of course, that's why we're here today. So I did find the questions now. And so I'm going to go back to this one for you, Debbie. And it was about, and feel free, Keith and Shannon, to answer too, but what solar assessment tools do you use on site to help figure out these kinds of things?
Yeah, thanks for asking that, Brett. And I did type in the chat box.
That's okay. You can answer it though. Yeah.
That I mentioned PV watts, and so I could have led to that confusion with the last question. But if you're looking for what state you want to live in, the person had asked on site selection, then by all means go to PV watts, and it'll show the resources, kind of like what you talked about, Brett. But in addition to PV watts, I took a zero energy design course by Mark Rosenbaum, and I think, or Mark Rosenthal, and I think he still teaches that course. And in that, he did a demonstration of how you could take the data from PV watts. You can export a spreadsheet, and then you can see all of your heat gain on whatever side of the building that you're looking at. So for those who would want to, geek out in the spreadsheet, there is that use of the tool as well.
Did we answer Jacqueline Gillette's question? When using BIM on a design, is there an analysis program that is more accurate than another? For instance, Insight or Cove tool? That's question one. And then question two, is it better to design without trying to utilize PV at all, or use PV as a last-ditch effort to reduce overall EUI? So I'll answer question two, and then I'll leave it to you guys to answer question one.
I wanted the second part, but go ahead, Shannon.
So for question two, Jacqueline, I would say a conservation first approach is always best, because just like the greenest building is the one that's already built, the greenest energy is the energy you don't use. So Keith or Debbie, do you want to take a stab at an analysis program more accurate than another in BIM design?
I'll make a stab
Sure.
at it, but as a qualification, I'm a residential architect that works with very simple clients on modest budgets. So I don't use high-end, more complicated software, and so I'm not familiar with the Insight or the Cove tool, for instance. What I do here, and I think Shannon, you had alluded to this as well too, that the WUFI that can interface with Revit. I've also was looking at another software, and I didn't get a trial version, so I wasn't able to cover it for this session, but CFERA is also a pre-modeling early tool, and they said the same thing, that Revit kind of was making it a little bit difficult to pull in the models, that they actually liked starting with the SketchUp and going backwards because of the simplicity. So I think that's what you were saying, Shannon. So
yeah, and this is a great segue actually into Thomas Allman's question, which is, can WUFI be used in Revit models?
So, you mind if I?
Oh yeah, go ahead, Keith, for sure.
That's question one. So in my presentation, I crossed out the static models, and I think that is really important. It can be difficult from a software website to figure out whether the software is static or dynamic, but to accurately include passive solar heating and passive cooling, you really need a dynamic model. And if you don't see thermal mass as an input, that is a strong indication that it's not a dynamic model. Static models, a lot of them neglect thermal mass, and you really need to have the thermal mass model. The models that I showed on that one slide that are the more simple building related models are BOPT, EQuest, and WUFI Plus. And I know that those can do a reasonably accurate job of modeling passive heating and passive cooling.
Yeah, so I was segueing right after that, thank you, Keith, to the question, is does Revit have a WUFI plugin? And it does, and it's been around for years. But for most of the professionals that I've ever spoken with who use Revit and use WUFI and use SketchUp, they still prefer to model quickly in SketchUp to get into WUFI.
Hey, great, thanks. I'm back here again.
Yay!
Got kicked out for a second. Unfortunately, I've the Q&A has vanished for me. So if any of you,
Oh, I have it up,
yeah,
Brett, if you want.
yeah, if you can still see it, feel free to start answering some questions. I've got a couple other questions here, but feel free to.
And I can throw them into the chat too, if you like.
Yeah, I do know.
The next one I see is from Timothy McBride, 1242. And Timothy said, Shannon, the old motto was in solar to design as solar passive as possible so active solar can do the rest easy. What about the zero energy building? And how does this type of shelter differ from a 100% off-grid passive active solar home? So I think they're speaking about zero energy building ready, or the zero energy ready home. I hope that's what you're talking about, Tim, but feel free to add comments in the chat.
And I think just to add, I think he's talking specifically about comparing passive solar to net zero, like total net zero. So DOE zero energy ready, of course, stops short of net zero, right?
Yeah.
But what are some of the differences there? How do those compare? I think if I'm reading it right, so.
Okay. That's a better interpretation. I agree. So 100% off-grid passive active solar home versus a net zero energy home is, I believe, when you're off-grid, and you guys, everybody chime in, but when you're off-grid and you are only using the energy that you're creating on site, you don't have to offset. But if you're doing a net zero energy building, you can use energy from the grid and offset it by buying renewable energy or buying energy credits. And there are different schools of thought on how effective that is, but I believe that's the difference. Any other comments on that one?
Let me just mention, if you are doing a really great job in your net zero and you're producing your own electricity that's equal to the amount you use, or maybe even selling some back to the utility, then whether you're actually carbon zero depends a lot on what the utility is doing. And right now in the US, the average is around 60% of our electricity is produced by fossil fuels. And the estimate is that by 2050, we'll only be down to 44%. So during the night, when your photovoltaic panels are not working, the photovoltaic panels for the electric utility are not working either, you're using electricity that is, at least in large part, produced with fossil fuels. So I think that's something to keep in mind, that if we can, I think there was another question related to this, reduce our load as much as possible before we add PV, then that's probably the best thing to do right now.
Mm-hmm. Yeah, and to add and to segue into the next question, you mentioned again at night, right? You're using the grid, you're using, unless you have a battery, right? You might be storing up in the day and then using your power at night. But that's going to be hard. I know it's hard for me when we're in the middle of a heat wave and I'm cooling all night, right? Which is still rare, but that's where, I'm using a ton of, as we speak, just, for those of you watching the recording, we're in the middle of a major heat wave here in the Midwest. So we're cooling throughout the night unless we've got a good passive ambient design. But on that note, the questions that were multiple questions came in here. I saw them all, so I remembered them. Is in these design tools, how many of these types of tools are planning for future, where we spend more time in heat waves and potentially cold waves? And how is that being accounted for in the design process? So, Debbie, I don't know if you have any thoughts to start with that first, and then we'll we'll move on.
Well, no, that's a great question. And that's why I was excited about what Keith is doing, is that he is, bringing to attention that we need to use a more up-to-date, behind the scenes amount of weather data that reflects the higher temperatures. I think right now TMY3 is the most current, broadest with the range of temperatures. And maybe I'll let Keith talk about this, but he was talking about another level, TMYX, that would take into account this month in Michigan and what you're experiencing, as well as maybe what you might have experienced, back in January as well. But to my knowledge right now, I don't think any of these modeling tools are taking the latest into effect. So that means you're back to common sense, not relying on the modeling tool to tell you that. You look outside, you know how hot it is. If you want to err, especially if you're a hot-natured person, I'll ask that with clients a lot. Are you hot-natured or cold-natured? And we might design the building differently based on that particular answer. So just paying attention to details and common sense for now.
Yeah, so the latest TMY data goes up to 2022. So it uses 2022 data plus the previous approximately 20 years. And, it was asked, well, why don't we use future weather data as best we can predict it? And people have started to formulate ways of assembling future meteorological year data. But right now, there's no archive where designers can go just download the data and use it. Right now, you have to formulate it yourself, especially if you want to design an ambient house where you need the extremes and not an average, typical meteorological year data set.
But, and Shannon, how
the National Solar Radiation Database is thinking about archiving future meteorological data.
Yeah. And Shannon, we look at those projected loads for each area that we saw in some of the passive house tools, the CEUS tools you showed us. How do you think through, okay, this is the load as of today, but what is it, tomorrow? Right. And what are your thoughts on that?
How do we future-proof? This is my favorite questions. Because anyone who cares about passive house cares about all these other things as well. So part of future proofing even takes the next question into account, which is, how do you take into consideration latitude, longitude, warming climate, trees, shrubs, grass, water, solar, when you care about future proofing, care about all of it. And so passive house is looking at doing the best with what we have right now to mitigate all of our energy use and get ourselves to a whole building and systems approach to achieving zero, so that if the sun is not out, we are still super efficient. Or if we live in the woods, we don't have any sun, we are still super efficient. And so anything that your site can offer you to get you closer to zero is what you should take advantage of. Like Debbie was saying, common sense. But Passive House does that with that envelope first. So it's a passive conservation first approach by getting the air tightness and super insulation and better windows and orientation shading. And then any active systems that you need to run, making those as small as possible so that your batteries can be small. You can have just a couple solar panels or wind turbine, hydro, whatever you're using to offset that energy use.
Keith, a question came in for you on ambient. Is there any kind of third-party verification that will be into play on that, or that's looked at, or a way to verify this is actually done correctly?
Yeah, thank you, Andre, for that question. If you go to the website on my last slide there's a white paper that we wrote from results from a workshop. And one of the recommendations is that we should have a certification programs for houses that are getting to 100% ambient conditioning, 100% hot water, and you could think of other things as well. So it's a great idea. So thanks, Andre. That's something that we're thinking about.
All right. Well, we are at our time today. So I really appreciate everyone for attending and all of our speakers here. And maybe just real quick, and I'll go to you, Debbie, where can people go to learn more, contact you, and what you do with passive solar?
Oh, okay. Yeah. And again, thanks everybody. Oh, that's the slide that I was looking for. Okay. So yeah. So you see Debbie at sunplans.com. If you have any email, you can email me questions there. My website is sunplans.com. All fairly simple. And I look forward to continuing this conversation around what I think is a very exciting subject that shows kind of how geeky I am. But hopefully GHI will be leading the next step in this. So send comments related to the next step, where you think we should go after this webinar. Thank you.
All right. And yeah, Shannon, where can people go to contact you and learn more?
Well, I've dropped my LinkedIn in the chat a few times, but you can show up on Source 2050 or Passive House Accelerator, or email me at shannon@sandersondesign.net.
Great. And Keith, where can people reach out to you?
My email is there, and I just want to say, if anyone knows of an existing house that is already 100% ambient conditioned, let me know. I'm trying to put together a database of these buildings so that we can promote them.
Great. Debbie, Keith, Shannon, thank you so much for your time. To all of you, we'll see you next week. Have a wonderful Juneteenth and summer solstice. And for those of you in the Midwest and Northeast, please stay safe and stay cool. We'll catch you next week. Take care. Bye.
Thanks, Brett. Thanks, everyone.
Thanks, Brett. Thanks, everybody.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.